So, welcome everyone. Today's QuMat seminar is given by Alejandro Silhanek. He comes from Argentina. He did his PhD in Bariloche, which is a kind of mythical place for physics in general since the 50s. And then he migrated to Europe, but he went to the US before, after?
Oh, in between.
In between. But he spent a long time in Leuven, just a group of Moshalkov, looking at superconductivity. Some of that will come into the next talk. And been in Liege almost as long as me, since 2010, 11. Doing, building a group in nanofabrication and experimental physics. He'll tell us about, shows us some junctions that are made kind of to order through electromigration. Please, thanks for coming.
Thank you very much, Matthieu, for the introduction. It's a big pleasure for me to be here. I think I've been here once just to change train. So now I think it's first time I have the opportunity to see at least the campus. So I'm going to talk today about electromigration from pain to gain. In Belgium, migration is a very hot topic, from pain to gain as well. So you might draw some conclusions, analogies, but I will talk basically about electromigration in system. I will start from scratch. I will explain the very basics, and I warn you, I'm an experimentalist, so there is no formulas in my slides.
We warn you, we are not going to push that in the audience.
So there will be only, it's like only images over here. So let me start with just introducing a bit our university. I think Matthieu already told you about Liege.
No, I never mentioned Liege.
Never mentioned.
No longer exists.
That's what
Okay. But Liege University, I mean, it was founded in 1817. At the time, Belgium was not Belgium. So actually, you correct me.
It was founded by the Dutch.
It was founded by the Dutch.
By the Dutch king.
Yeah.
He said
University over there. So yeah, exactly.
University.
So we have about 20,000 students over there, and too few physics professors. So we have a lot of teaching and a lot of involvement directly with the students. So this is to have you an idea of how the city looks like. So city is about 10 kilometers from our campus, and it's the most beautiful campus. Very nice forest. Camino de Santiago starts from there. Also, and this is my office. It looks like a typical building, gray physics, So my group is growing up, and it's a group with a lot of diversity. We work in solid state physics, and this is the boundary between a lot of disciplines. So what happens to us is, at the beginning, I just recruited physicists. By now, we have engineers and we have chemist people background. So it's quite diverse, very rich in that sense. There's a big problem is the gender equilibrium. It's something I do not manage to do it well. So only males on the picture. And most of the work I'm going to present today is thanks to these two gentlemen, Stefan Marinkovic and Daniel Stoffler from chemistry, the other engineer. So we do a couple of different things. So we have basically experimental facilities. I will not go in detail because I don't think you will enjoy this part if you're mainly theoreticians. But we do some tiny simulations here and there. Just complement our results, and we have a sort of diversity of research lines. So some of the topics that interest us and some of the collaborators. So we do a lot of imaging of magnetic fields on superconducting samples and ferromagnetic samples, but a big scale I'm talking about. So just to give you an idea, this is about 2 millimeters. We have some collaboration on plasmonic metamaterials and also in DC metamaterials. How can you basically cloak something from a magnetic field? So magnetic field lines go through without deformation, so you don't detect the magnetic, there is something there. So you do sort of invisibility, but magnetic, okay? So we are recently developing also a line of research in superconducting resonators because there's quite some interest for quantum computing. And some magnon is just starting recently as well, propagation of magnons in ferromagnets. But I'm going to talk today about this guy here, like electromigration, because we spend a bit more time on that. I think we collected a couple of nice findings of it. So just to give you an idea of the outline, I will start from zero, scratch from electromigration. What does it mean? How does it work this in monoatomic materials? So how this phenomena can be implemented to affect materials of one single family of atoms, and what happens if you go to very complex materials, and I will show you some examples that we were working lately. So electromigration is simply the migration of atoms induced by the current. So it's something that you never heard about when you go to the school. Basically, they teach you that if you send the current, so here, for example, we have an electric field in this direction, electron goes in the other direction, and electrons, bump into impurities, or, atoms are shaking, and electrons are deflected. But actually, there is transfer of momentum to the atom as well. So what happened to the atom? So we never discussed that. And it happens that if you have a lot of current on the system, you actually have a huge wind of electrons coming to the atom. And sometimes it's too much, and they can't even move the atom. And so you end up moving the atoms with the current. So that's why I call it also electronic erosion, because you can erode the material by moving away the atoms from the place. Okay, so that's simply the electromigration. So once you look at the classical picture, when you apply electric field in that direction, you have an ion here, which is a positive, is a foreign atom that's well bigger, and therefore you have a direct force, which is, but the force produced by the electrons is also proportional to the electric field, because more electric field you have, more electrons you have, and therefore the total force is something which is proportional to the electric field. Okay? So that's, and sometimes, this is still a huge discussion about how much of the force comes from this side and how much comes from the other side. And even if they are additive or not, that's not clear at all, because it's not simple calculation. Many people thought that this force is zero because it's completely screened. Yeah.
You call it erosion. Does this suggest that it's irreversible? And there's some entropic content as well.
Yeah, there is irreversibility. There are forces. We can talk about forces in quantum physics, but there are how to say, conservative forces in the system. Yes, there is a kind of irreversibility. Okay. Yes.
And you said big enough current, so electric field, how big are we talking about with respect to the usual electric field where all the electrons can move?
What was the question?
So basically,
how big is big enough for? Right?
Oh, I will just give you a number, exact number. Just give me a second. I will show you.
But it's totally material dependent.
It's totally material dependent. Yes, that's part of the talk as well. Okay. So the first question is, why we never talk about this? Why don't we see this in real life? And the reason is, if you go to house appliances or electrodomestic things, you basically once you reach the current density of 10 to the 4th amperes square centimeter, what happens is the temperature of your wire goes above the melting. You just melt the material. So the current density can never go really high because you cannot evacuate the heat, as simple as that. Okay, so that's why electromigration, you will never see it in the normal wires. Let's say that's how a fuse works. So now the problem comes when you go to small dimensions, and these are integrated circuits. There, heat evacuation is very efficient, particularly because they are very small wires which are solidary to a substrate. So once you heat bump, they goes away. And in that case, you can reach currents of the order of 10 to the 8 amperes per square centimeter, which is huge, without melting the material. And at that current density, you start to move atoms. Okay, so it's something like it's not a curiosity, I would say. IBM spent billions to solve this problem in the 60s. The first computing didn't work at all because of this problem. This problem continues today because you are doing integration of circuits in 3 dimensions with the heat evacuation is even more difficult. People are trying to use flexible substrates with everything becomes worse as well. So it's a continuous problem that is of, I would say, currently necessary to study. So what happened with electromigration? So basically you apply very high current density, answering your question, this order of magnitude, and you are far below the melting. Okay, you are heating up, of course, but you are far below the melting, and you start moving atoms. Okay, and when you move atoms, this is how it looked like, the system before moving atoms, and you can end up either moving them away completely or actually piling up them. Okay, that depends on the conditions of it. So if you have that, your circuit does not work anymore. If you have that, this might touch another layer and you have shorts, so it doesn't work anymore. Okay, and that's actually what happened at the very beginning of this problem, because I mean, how easy you move an atom, that has to do with the binding energy, and the binding energy is proportional to the melting temperature. So they used aluminium, which has very low melting. So with small current pump, you start moving it. Okay, so it was bad design at the time. And I think this is just to show you that actually you, I mean, you don't need to contact your sample to move the atoms. There was a very interesting experiment in which Liege from Israel, he put a substrate, which is titanium nitride, which is a bad conductor, okay? Very, let's say, high resistivity, and on top a piece of aluminum, okay? So what happened is current comes through the titanium nitride, but once it reaches there, you have 2 resistances in parallel. Most of the current goes to the low resistance path, okay? It goes up to the aluminum and then comes back here. And if you apply enough current, this current over there can be big enough to move atoms. And what happens is they can move out this part to that part over there. These are his original images, very old, so you don't see much clearly. But these are more new ones. So you see the structure before applying the current, and after that, you see how this receded to here and gets accumulated to the other side. So it's something that you move it and you see it. Okay, is
it like a wave?
Wave.
Yeah, or is it really just moving of? Just
It looks like it's get compressed even.
Yeah.
It's not the atoms from the left that make it all the way to the right.
Yeah, indeed.
It's not.
Little by little.
Yeah, I mean, it's indeed that exactly. You are moving one thing and you are accumulating, but indeed you are moving. Basically, you are removing from here. Those are not anymore.
But are those atoms the one that?
No. Typically, they are pushing others, and
It's like a domino effect.
Exactly.
I'm curious about the electron wind. I mean, because the electron wind also depends on, I guess, how much it interacts with phonons and stuff. So is there a double amplified effect here if you have a bad conductor or a...
Temperature plays a very important role because this is a thermal activation process. So, and it's something you cannot get rid of it. So it comes together. And I'll show you later, it's even more complicated because there are other, I mean, this guy, what he shows basically is that once you get too short, it does not work anymore. Because it happens is that you build up a gradient of concentration. It becomes very dense on one side and very porous on the other side. And that actually makes a gradient in the opposite direction. So at a certain moment, when it's too short, it doesn't work anymore. Okay, but I'll show you an example of someone who used this to make nanowires. So what we did is, once again, we have this titanium nitride bad conductor. He made a hole here. You have aluminum layer. This is the aluminum line. Okay. You just apply current. Current comes through the aluminum. When you reach to the end, it goes to the titanium nitride. Okay. And he pushed. Tuk, and get a nanowire popping up all things. So this is how it looked like in real life. Okay, so this is nanoscopic, and then we make some theory, everything corresponds to a grain boundary and stuff like that, but it's very, yeah.
Can you make a STM with this thing?
That's a good question. This is about 10 micrometers. I don't know. That's a, yeah. One thing you could do is try to clean your STM with the big current. But okay. But okay, this is a very high current, and the example is going to give you here is one of the material I will show you at the end. I just plug in the resistivity of the material, current density we need to move atoms. I just make the product, get my power density is about 5 gigawatts per cubic centimeter. This is about the power of the nuclear plant we have in Belgium in 1 centimeter. Okay, so it's a huge amount of stress you put on the sample. Okay, more or less it's the same energy you need to ablate the material with the laser. Okay, so it has to be something of that scale. So what we do is, so this is the part, and it has been for the technology, the part that we call the pain. It cost a lot of money, it cost a lot of problems. I was all negative. So you say electromigration and people start crying. Okay. Now we are going to the gain. And the gain is the part that we say, well, let's try to do something cool out of it. Okay. So the first thing we need to do is to know exactly where we are going to electromigrate. And it happens there is a big, very well-known law that is called the Black family name. It says that if you make 100 devices, 50 of them will fail due to electromigration with a time failure, which is given by this equation, which is activation energy, temperature, and the current density. So you want to make them to fail quickly, just increase the temperature, reduce the binding energy between neighboring atoms, or increase the current density. Okay? So we play with that. We do a small constriction, a few grains, and we know that here the current density is maximum. Okay, so it's going to fail there, and so we know what to look at, because if you do STM, you know how difficult it is to navigate in a sample of 1 millimeter size. It's too big, So and now what you have to do is to apply big current on, see how the atoms move. Okay, it happens is not that easy, because once you start moving the atoms. I think I made a talk that will last for 3 hours. So, Chairman, please stop.
Okay.
So I don't know how to keep this, but so basically you start applying a current. The idea is the following: that's the electrons moving. You heat up locally, and then you start moving the atoms, and then you can make a constriction of the size you want. Okay, that's the trick. There is a problem here. The problem is that once you start forming voids here, the current crowding or the current density goes up, the temperature goes up, the resistance increases with temperature because it has a coefficient which is positive. Okay, it's a metal. Then you generate more, and this is a positive gain loop. So you end up, like, without willing, you will end up blowing your sample. So basically, if you measure resistance versus current, you heat up the system. When you start to electromigrate, explodes. I show you this is the case because we try. So sample before trying, sample after trying, all blow in the air. Matthieu.
Your initial slides had some comparison to the melting temperature, but it's the melting temperature of a bulk. This is
of
the bulk.
No, not necessarily.
Okay. Because here, in a nanoconstriction, I can imagine that the melting temperature would actually be much lower. And from the look of it, I don't know what timescales are, but this could actually count as partial melting.
You're totally right.
Is there really a distinction between electromigration and melting plus some
yes. There is a clear. You can see it. You can see the melting. It has a different shape, but still melting. I agree with you. Decreased, but it's not like it goes half. Not at the scale we are playing. So I have some movies to show you.
Think of it like melting is in some sense an isotropic process, whereas electromigration is
exactly, it's directional. Totally right. Very clever person here. Yes, of course. You're all too. So this is another example. Two big pads, and there was a small bridge here. You don't see it because it explodes. Okay? So it doesn't work. So what we do is we try to control that. So it's nothing complicated, a stupid feedback loop. But what the point is, once we get to this point, what we do is if we see that the system wants to explode, we reduce the current. Okay? And it's a fight between the system and our software is trying to explode and you don't want, it's like, like Chernobyl, and then if you don't do it well, it explodes. Okay? So, and then we build up going through this curve, but it's a fight. It's really a fight. So you don't go smoothly. You go like ticky, 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 ticky. Okay? Consistent. And then in that way, we can go up onto the resistance to the system. So let me show you how does it look like in real life. So this is a case of aluminum. Okay? Look at the black curve is experimental data. Vertical axis is the resistance of the system. This is the current we are applying. We started with the system very cold. We cooled down to 1.5 Kelvin, and we start applying current. So what you see, resistance goes up. This is just because aluminum has a positive system coefficient. Okay, it's just if you turn off the current here, you just come back on the same line. It's totally reversible. Yes.
Just a technical question on this. So is this done now at constant voltage? Or, I mean, what is the parameter that you're having? Are you actually actively amplifying the current, or are you just keeping the voltage fixed and letting the current?
Does not matter.
Okay.
Does not matter. I can explain you in detail with the Kirchhoff law why it does not matter. But both, because indeed, there are some people who say, if you apply voltage, once the system goes down in size and the resistance go up, it limits the current, so it's self-limited. No, that's not true. That's only true theoretically. But since you apply voltage far away, all the leads dominate your actually value of the current. So it's not the constriction that dominates anything. So in real life, typically we can apply either voltage or current. Both terms. Okay. So what happens is you get to this point, and at that point, estimation for that we use, just console simulation. We get an estimation. Sample is heat up to 230 Kelvin. So it's not even room temperature. Okay, we are below melting. 230 is below room temperature, and we start to electromagnet. And there you start going like so. Every time you need less and less current because size is getting smaller. So. And then once we get there, we stop and we make an image of the sample. So this is the original sample. At that point, it looked like that. We make this, we stopped, look, we see where we make a hole on the system. We do it again. We see another hole on the system. But it's getting narrow. So this is by far the limit we can do with electron beam lithography. So we can go down all the way to basically single atoms. We can get quantum of conductance doing this. Okay, so it's a lot of control on the system. So we apply this method to, for example, in the case, I will go very, very quickly, to narrow down superconductors and detect the transition from what we call thermally excited phase slip to quantumly excited phase slips, because we can narrow down that. We cannot do that via normal fabrication. It's basically impossible. Okay, so this is an example of application. Now, the cool part is the following. Here is another case. This is again aluminum. We started from here. This is once again, you stop here, you come back on the same curve. That's why it's always smooth. This is just heating up. Get there, and then you want to blow up, but you start to fight. Okay? And therefore you go up, 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 and then you see we can get to 200. So it's quite high. It's few 100%. Okay. And then we measure the resistance versus temperature because it's a superconductor aluminum with a TC of 1.3 or something. So you see the superconductor transition going. Okay. And then you look at the image and you see this is where I remove the material. But now instead of sending the current like that, we reverse the current. Okay. And what's going to happen is we send back the atoms we took from here and we put them on the same place, which is kind of astonishing. Let me show you. So this is what happened. We started from that resistance and now we anti-electromigrate, we call it healing that, and then you go all the way down. And then you recover very nice transition. Right. So the system, and then you make an image. And indeed, is a bit blurred because every time you make an image, you put either carbons contamination on top, but you see it's filled. That part. Okay. Yes.
But first you lost a piece.
Yes.
Where is this coming from now? From
But
from the
when you move the atoms here, you move them to somewhere out of your voltage contact, and you put them back.
They're not completely lost.
I mean, you see the image. Oh, it's amazing. It's amazing. It's amazing. I agree with you. Okay. So I show you. I mean, I spoil the superconductor. I make it nicer. But now I do it again because you don't believe me. So I start from here. It's the same sample. I go all the way back, and then I spoil it again. I put the current in the other direction, and I get it back again. I can go back and forth. I remove the atoms, I put them back. It's cool.
Up to which side you can hear, like out, like
How many times?
no, or say
How
one,
distant?
but also like the sides of
How big they
nanometers,
diffuse?
oh, yeah, because like imagine you are I don't know, in space, there is a damage on your spaceship and you want
Yes.
to repair it, no? Without going outside. Wait, like in the science fiction.
Yeah. So they move to so it depends on how much you apply. They can move to very long distances, on the order of 2, 3, 4, 5 microns.
Okay, that's big.
Yes.
So that what comes back is really the piece that you have.
Some atoms come back.
So yeah, it's not exactly the
I tell you the truth. I tell you the truth. The question you have is how the hell they know where to go and sit over there?
Yes.
There is a kind of stress in the system. Don't forget you have a substrate. There are particular places where you build up a grading which is not natural. Even what happens to us in the past is we did that all over the night. We turn off the equipment and we come back in the morning and it's completely healed again because they want to go there. So the current just help them to go there. It's a self-healing that you're. Of course, they don't feel in exactly the same places. Okay? So you will see. I will show you. There are irreversibilities, unavoidable irreversibilities.
This is a superconductor, right? So
Yeah, superconductor. When you electromigrate, it's never superconductor because you cannot. Okay.
so that's why the logarithm of the resistance has that.
I'm showing the superconducting transition because it's the most sensitive thing to what you are doing to the sample. You modify the normal state, but superconducting transition is the witness of the quality of your junction.
Which is at 1.36.
Yeah, something like that. Exactly.
So the so the
There's
difference
something
is shape.
special about the electromigrated atoms in that they're less bonded, or they tend to diffuse more. Everything you can see, like if you just follow up a few of these little fights, instead of going all the way up to 200 ohms, can you see small movements of mass, and is it different quality somehow? And it's not bonded, it's not as crystalline as the rest, and it's maybe easier.
Yes.
It's the first
It's-
stuff that's going to move.
I agree with you.
No?
There is a mess of there is a mess of physical changes you do to the sample. So sometimes in aluminum, I think you really move them very cold. In others, for example, you go to a refractory material like niobium, the bonding is very, very strong. It's very difficult to break and move. And then you have a combination. You have an annealing, we call it. So you change the grain size, you change the quality of the sample, and you also move the atoms. So all comes together. And there is very difficult to make a distinction. In aluminum, is like aluminum and gold, platinum, those are very simple to work with. Other materials are a bit more tricky. And it can be that you have a lot of physical effects. Yes.
I was going to wait for the idea, but I think that all makes sense. So what is the relationship with Yao heating? Because it sounds to me super.
With sure,
Yao heating, yeah.
Is totally needed. Is there? Is the activation energy you need to move the atoms? The temperature plays a role over there.
Yeah, what do you mean?
But it's directional. So the current plays is what he says is totally right. If it's just temperature, it's very isotropic.
Yeah, well, maybe it's jargon used in the field, but so in the field of graphene and carbon, gel heating is usually used to anneal or
Yes.
nanostructures.
Exactly.
With currents.
Exactly.
So it sounds to me like it's like very similar, just
No. Nothing to do. Well, a little bit. But yeah. Sure heating, we cannot get rid of it. It is there. Okay. And that is gonna in graphene is use this method to clean. But even better, in graphene, you can even direct in which direction you want to move. For example, if you have adsorbates on the surface, you can move it because current is going to go through graphene. You have an adsorbate, it's going to go on part depending on what you put on top, and it can drag it actually directionally. I mean, heating, of course, if you hit the center, they will move away symmetrically. But I will show you an example because we did a sample where we look at the right and the left, and then we see the difference. Okay, that I think it becomes a bit clear. But Joule heating is there. We cannot avoid it. I wanted to show that some people also did this in the Netherlands. So I think this is coming from Delft. And I show you an example where we do this, not fighting, but with pulses. So it's another approach. It's very experimental. So in that case, if you do pulses, it's much easier to see after you move the atoms, because you put a big pulse to move the atoms and then a small pulse to see what happened. Okay, so it's a kind of pump probe current rather than with lasers. Okay, so basically this is the maximum resistance at the top of the pulse, so you just get the Joule heating. This is basically this curve, and this is the small resistance you get out of this measurement. So it's when the system is cold and stable, and after applying a big current, and then you see nothing changed, and you reach the electromigration current, and then you see the system start to be modified, more atoms. So, and then we can do that. We can look at this one. We can apply a current, move the atoms, revert the current direction, and then we'll start from here and put it back. Okay, and this is what we did with this concept. So we move the atom, we put it back. We move the atom, we put it back. We move the atom, put it back, and we did that thousands of times. So you say how many times you can do it? Thousands of times. Okay. So it's very, very. But if you look at the end, you see that is irreversible. Okay. There is damage on the system. And even more, I mean, I will not go, I'm going to go to the funny simulations. You are two theoreticians, Verstraete. But the images perhaps is not very good on the beamer here, but this is essential. And then you see there is, and I don't know if you are right to see here, there is a small black spot there. Those are black spots there, those are materials removed. But if you look carefully, there is no current density over there. So you move atoms, even there is no current, because you build up stress as well in the system. So there is, besides electromigration, you have migration due to gradient of concentration and due to the gradient of temperatures, thermomigration as well. So there are many effects that play a role. So Okay. So let me show you one image live. Live is not real live in permalloy, which is an alloy of nickel and iron. So look at that. So you see some annealing here, the big grains becoming, and then you generate that. Okay. So you can find it in Wikipedia. So the melting, this is a bit of the melting temperature of nickel and iron, and this is a recrystallization temperature is a lot lower. And then there is something you can see. You see that the grains get bigger, small grains, they get bigger. So, and then you move the atoms later on. So there are different stages, as you say, Matthieu, of different physics and different quantum. So people. We have done that, for example, to modify superconducting squid. So you make a squid. This is niobium. You have a junction. This junction is typical of superconducting squid in niobium. The junction is irreversible. If it's irreversible, the current voltage characteristic is irreversible. Is basically useless. So you need to modify the junction, but it is already too small. You cannot do it simply with something. So you just pass big currents, we modify by electromigration, and you make it work. So this is a real application of that. We did that in aluminum as well. We work with 3 junctions, and you can select which one you want to change as well. No problem at all. Just because you combine these 2 currents, build up together, and then so these 2 are below the electromigration, and this is above, and then bam, you do exactly what you want to do it.
In the top one,
yes,
you're adding material and increasing the resistance.
You are destroying superconductivity there. It's actually, this is niobium, so it's a bit tricky. It's a bit of.
It's not just constriction. Right?
No, it's also oxidation, local oxidation, because it's made on air. And so you change the properties and you make the weak link weaker. That's what you want, reversing. Okay. But you can also make a heater. For example, in this sample, we wanted to have a superconductor. Next to it, we wanted to have a heater of another material. Difficult to do because you have to do overlay to the position. No, we just take the niobium, we electromigrate it. You don't see very clearly. And you change the properties here and becomes a normal metal. So it's a handy way of. Some colleagues have even used it for making antennas and generating. Every time an electron jumps from here, they have a directional variation. Yes.
How much time do I have to wait until we electromigrate if I want to, for example, niobium change it?
No, well, I mean, it depends on how carefully you want to do it. But no, this is.
Are we talking about
half an hour?
Yeah, okay.
Something like that. Okay, so far I told you about what happens if you have a material of one single atom. Right? Very easy to mentally. Yes.
Quick question about this. So now you told us earlier that if you did electromigration and then you waited overnight, it restored itself.
Yeah, not always.
No.
We have seen that.
Okay, you've seen it. It's not. It's not a generic process.
No, not always. No. It has a small relaxation. Basically, it gets stable, probably metastable state. So I wanted now to show you what happens once you go to a system with different atoms. And the system we chose is YBCO, is lithium barium copper oxide, high TC superconductor. There's a very complex system. And basically, what you have to see here is these oxygens, which are the small blue balls, and copper, which are the big ones. This is the fault of my student. Should be the other way around because it's ionic size should be oxygen bigger than the copper. Okay, but so these are chains we call them. Okay, and these are planes, copper oxygen planes. Okay, superconductivity coming from these planes. But once you change the oxygen here content, you actually removing that one. But when you remove that one, putting more oxygen here, basically what it does is to suck electrons, okay? The affinity of oxygen is to suck electrons. So when it sucks the electrons, it comes from this plane. And this is a hole conductor. So basically you generate more holes here and you improve superconductivity. So you have this plane and so people knew already. I mean, when you change oxygen, it's going to be from here. When you change that, you change the properties of the material. And the rich thing about that is that this material can go from insulator to superconductor to metal, bad metal, antiferromagnet. So just changing the oxygen. So we say, okay, that's the knob you have to change the properties of the material. Why don't we just electromigrate and try to move that oxygen with the electromigration, right? The first thing you have to understand is how the current flows this material. So that was already done. It's an old topic. So people realize that if you apply the current in what we call p-axis crystallographic direction, both planes unchanged conduct electricity. If you go in a direction, these are inefficient and only the planes conduct. So people basically deduce simply that 60% of the current goes basically on the chains. So when you apply a current, most of the current goes through the chain. That's what it is. Okay? About half, a bit more than half. Okay? So we have enough current on the plane. So the idea is to apply current and try to move this. Once we put it here, the can diffuse very easily because they are empty places. Tick, 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 tick. Okay. Why is that interesting? Because there is a big fight on this system to understand the phase boundary. Okay. So basically temperature and hole doping, how many holes you have on the plane, and how many holes you have on the plane depends on how many oxygens you have on the chains. So if you move the oxygens, you basically can sweep this axis. Okay. This is what I'm trying to go fast here because of time. So what we propose is to people so far build up this phase diagram by making a sample with this oxygen content and this oxygen content and this oxygen content every time under different oxygen conditions, different samples, different, What I'm proposing is, no, we just come to the chemical formula. This oxygen doping or whatever, delta you have over there, is now a function of current. So I have only one sample. I apply current and I change this. And I can build up the whole phase diagram just with current. And even better, I can put them back. So some people, of course, try to do this with the ionic liquid gating, metallic top gating, ferroelectric gating, all that work. But this is purely electric field effect, and this needs huge electric field, and it's very limited to the surface. I'm proposing something volume scale. So these are our samples. So YVCO is the yellow stuff. The gray you see there is just we put silver because you want an ohmic contact, so you don't want shoot heat in there. And if you look at the center, it looks like this. And this is where it comes to your question about directionality. So I make a small bridge on the center, but then I make two other bridges on the side. So I can see where the oxygens are going now. Because I don't measure only this. I also measure what happened here and what happened there. Okay. And this is how it looks like resistance versus temperature. The pristine sample, so I didn't move a single oxygen, everything is monolithic, it's all the same. I put three curves where I measure the resistance of the blue part on the right, the green, the center, or the red, and you see all of them the same. Okay, so I started from a very clean sample. I apply a huge current, ticky, they change. The blue side, so all of them together, let's say the pristine, I keep it for reference, it's the black one. This side gets a little bit better. You don't see that, but if I do a zoom, it's clearly out of the noise. It gets better because I put oxygens there. The red and the green, which are this side, are destroyed. because I remove the oxygen from there. Okay. And better than that, I take an optical image. Here you have to concentrate when you look at this, the black part is your sample, okay? So this is the contact of voltage, this is another contact of voltage, this is the sample, okay? But then I see all this green part is where oxygen is missing, because it has been shown that when you remove oxygen, it becomes, the reflectivity decreases. So you can't even see where the atoms go with your eye. Okay, so I mean, not the atoms, but so and in that way, I mean, we go very quickly here. We try to put some points in the phase diagram, and we show indeed that they are not that bad. Of course, we didn't do a very good job. And some other colleagues from Sweden, Chalmers, they did more properly. They apply our technique. They are sample growers. They did very well. So the phase down, you can build up with that. And to show that we have oxygen really depletion, we did a bit of Raman investigation. So Raman, we investigate the mode in which these oxygen are moving, like the blue arrows here. Okay, these oxygen, we don't touch them with electromigration, but they are very sensitive. The length is very sensitive to what you have on the chains. Okay, so what happened is so delta is in the equation of YBCO is oxygen 7 minus delta. So the delta is 0, means you are imperfect conductor, superconductor. As delta increases, you make it more and more insulator towards the antiferromagnetic phase. So, and as the delta increases, so you remove more atoms, the z-axis of the unit cell increases, so it becomes a softer mode, and the frequency goes down. So it's very easy to detect how much oxygen you have. So we did Raman at these green spots. In the pristine sample, everything looks nice. You can even detect how many oxygens you have. Once you electromigrate, you see that it goes down. Okay, if you keep electromigrating, you can propagate in one direction. And this, once again, you can do it back and forth. So this is the same color code: blue on the right, red on the left, green on the center. And these are resistance as a function of the current, which is going positive and negative. So you're applying current, this. So you remove oxygens here, you put them there. So goes down here, goes up here. And on the middle, you see that the wave goes through. So this is why you see a dome. And then you put them back on one side and the other. So you can put the oxygen one side, the other, one side, so you can do it more or less reversible. I'll show you a small movie, perhaps, if that works. If you have epilepsy, you should not watch this. So you see, this is the wave propagating, and then you invert the current to the other side, and essentially you will see that it goes to the other side. It's not fully reversible. But then you will see that this is the differential that goes to the other side. There's just a few of them. And this is huge to be able to see. So it's very reversible. This is tiny. So it's just, to be able to make it reversible. So if you go very far away, it becomes very irreversible, if you do it, it's more or less reversible.
In these images now, it's correct to see that you actually had first depletion in this, let's say, fan opening up to the left.
Yeah.
And then you also got depletion on the fan opening up to the right.
Yeah.
But it didn't close on the
No,
left.
it didn't close perfectly.
It's still there, but it's not.
It's not as good as, yeah, indeed. This is because we push too far.
Okay.
Yeah. Yeah, so a bit of images showing the snapshot. I will not go to the detail. Just to show you, we did similar things on magnet. So it's a completely magnetic material, but basically similar formula. You change the oxygens, you change the magnetization now of the system, and we were able to also move oxygens over there and generate other things. And I think with that, I tell you more or less what we have done. The conclusions, I think the interesting ones, is that I think it's an appealing tool for fabrication, weak linking nanowires, modifying properties of weak linking squids, local doping can do with that as well, moving oxygens, fabricating nanoheaters, crystals, nano gap point contacts, antennas, cleaning, outgassing, annealing. So one thing, for example, we didn't have time to talk now is if you go to spintronic and you want to have a spin torque effect and you want to move, domain walls, you need currents which are very close to that. So to what extent you can ignore these effects? Okay. And I think it's very nice for fine-tuning quantum critical points in Wave-Zero, for example. And with that, I finished. There is a lot of collaborations, but basically I wanted to mention Stefan Marinkovic and Daniel Stoffel, our group of Leuven. We collaborate, and most of the high TC comes from Barcelona, but collaborate with a lot of very clever people around the planet. And with that, I close my presentation. Any question?
Yeah, oh, good.
It's a good question. You want to start?
Yes. So it is really rings a bell about like all the school electrochemistry, right? So when you are studying electrochemistry, you have the thermodynamical part where you know the spontaneity and also reversibility of a chemical process, and then you have the kinetics part where you can, study the scale of time where this reaction happens, but also you can reach an over potential, right? When you bring your material to the limit before you break it, you change it. So, this is done for obviously bigger systems. Could these well-studied parameters or limits when a material changes from one to the other be applied for these kind of systems? Because I feel like for the sizes and the lengths of time you are talking about, you are right in the limit, right? When you are from the macroscopic to the quantum limit. So I don't know if this could be in a way useful to predict, how this electromigration process would happen.
This I see it also like a solid state reaction. In some sense, I see also the analogy. So your question is more if we can learn something from.
Applying something that is already, well established or studied, or there are references and tables for different materials, and then because at the end of the day, it is a heterogeneous process because you have you have the interface of a solid, and then you have an it's in electronic, right? So then you have this exchange of atoms between at the interface of the materials. This is of course.
This is like a battery,
exactly.
lithium battery. Is the idea? I guess there might be a clear analogies over there. I didn't explore. My background in chemistry. I was very bad at studying chemistry, but probably there is analogies to draw there. Of course, this is not liquid system, but
yes.
it should work in liquid as well.
Okay.
Yeah.
Yeah, so in your conclusion, you write that it's an accessible technique.
Yes.
Do you mean accessible money-wise or accessible?
Very democratic. I'll give you all the software, and you just need to buy a few stupid. Everyone in every lab has the electronics to do this. This is why I found it interesting. I think it's a cheap physics. In that sense. Yeah. In principle.
I'm curious about let's call it precision.
Yeah.
So, I understand that you already have a bridge, so you can etch away, and then you can make the bridge narrower, and then you can, if you're really good, you can go down to the 1/2 level. But you're still very much dependent on your overall material geometry, how you, let's call it electromigrate etch in a sense. So how much flexibility do you have in where you actually etching happens if you have multiple?
Yeah, no, you are totally right. It's very, it's a random process. So if you have a normal wire, you don't know where it's going to start. It's going to start in a grain, and which grain, Is the defect at the border. I mean, that's the big problem. Actually, initially, when this happens, it was in the 60s, and circuits were like 1 micron, but they didn't see anything because the electron microscope was still, I mean, it's from the 40s, but it was not commercial device. So they just look at the optical microscope, they didn't see anything at all. So it was random, very difficult to spot what is going to happen. So yeah, so I try to show applicabilities for the lab for us. It can be handy for those using squids, for example. But yes, it's, to have it uniformly and stuff like that, it's more tricky thing. Yeah.
Is it possible? This is way more like a fiction, but would it be possible to have like exploit electromigration where you have like, let's say, a sample, then you protect a specific form of the sample, like a shape, then you electromigrate everything, so everything moves aside from the shape, because it is like screening from the rest, and then I create the form that I want. I have like a stamp that protects a piece of material, and then everything else goes away, but then I have
I mean, in principle, you're totally right. I mean, one of the way they found out to protect the sample is to capping with something. Because once you put, I don't know, silicon oxide on top, is a lot. I mean, I didn't show, but the activation energy of the atoms are I mean, the lowest is on the surface, and the next lowest is on the grains, in the grains boundary, sorry. And inside the grain is very difficult to move. So basically, you deform grains, and but so once you protect the surface, you become a lot more resistance to electromigration. Indeed, and this is one of the problems we have making the images. Because when you make an image, you don't want, but you deposit a bit of hydrocarbons on the surface, and the next image is more difficult, and it's, you know, our system at least gets contaminated very quickly. So you can do 20 images, and bam, difficult to do. I mean, if you do it a single crystal, there is almost no electromigration of the bulk at all. So.
It also depends on the position or whatever technique they use to make the
Precision.
VCO and the grain size and everything, the texturing.
Yeah, that is PLD, pulse laser deposition. So and also we tried 2 types on chemical deposition, and those are really nasty systems. If you look carefully to them, they look ugly. So it's not a nice crystal. Polycrystalline structure. Okay.
You presented the migration in YBCO.
Yeah.
Like you could choose which atom you wanted to electromigrate, but in practice,
because I knew already, because it was well studied.
It's known that the oxygen vacancies are easy to form in many oxides.
Yes.
But say you wanted to do something else, is there a way to get around it, changing the current direction or the overpotential or something like this?
Yeah.
Is there a chance that you could, in some others, I'm not saying here because it's probably very specific, but in certain systems, can you choose to electromigrate
selectively
for the other? And
I think it goes for them as a matter of binding energy, and I think it goes where the current flows, I think. Yeah, there's not a lot of control over it.
So in a compound that choose to move one, but not.
I mean, eventually in YBCO, we end up moving everything. So if you keep, I didn't show, but if you keep pushing, you make gaps and stuff like that. So you can move all that, but really selecting one, I'm a bit, I knew in YBCO was well documented that when you do, you only move that one.
Mm-hmm.
Yeah, because aluminum is just one.
Yeah, exactly. So
here,
you have an alloy, it depends on what you have. And it's very tricky. Actually, they found the solutions for electromigration in integrated circuits. It's by chance, typically. They just someone mixed up copper, a tiny amount of copper, and it stopped the electromigration. Now, if you take copper and you put aluminum, electromigration gets even worse. So, yeah.
And if you have like a multi-layer structure, in, for example, move only one,
That's something we wanted. There's something we wanted to try.
Okay.
Because we wanted to have. We were talking today with you about having superconductor ferromagnet superconductor to have spin triplet currents. So we and for that you need gaps which are like 10, 20 nanometers. It's very difficult to target. So we wanted to electromigrate only one layer, not the other.
Yeah.
It was one of the plans, but we found another way to try to do that. So we'll go for that one. Problem is you oxidize if you do it in air, you heat up a lot. So there are a lot more. When I tell you a story, it's very romantic. There's a lot of painful process behind that, you know.
There's pain in the game.
There's pain in
Has anyone done this on ionic conductors?
Like
Looking at really anharmonic systems like copper iodide tellurides or silver fluoride or silver iodides. There were some of them where at a reasonable number of a few hundred Kelvin or a few hundred Celsius, you can get one sublattice that becomes extremely mobile and really ionic conductor.
Good question.
And
Sebastian
I'll get
that's very hard to check.
Okay.
Perhaps I'm not aware. Yeah.
May I suggest we break and continue offline?
Sure.
Yeah. That's, thank you.